Okay, here we are. Welcome back. Happy Thursday. So I have finally finished grading homework 3. Each of you should have your feedback available inside the homework portal as I sent out over email this morning. In terms of upcoming due dates and such, so here we are on the 3rd of November. Nothing is due on Monday, but what you can be working on in the meantime, which is due on the 14th, so in 2 weeks, is homework 4, as well as an optional revision to homework 3. So if you look at your points and you're like, yeah, I'm good with that, I don't want to fix it, fine with me, if it's fine with you. Otherwise, you can submit your revision to earn up to full credit. So the only points you can't get back are any loss to lateness. Otherwise, I'll give you credit for fixing your work. In terms of homework 4, I've entertained questions from some of you who are not getting the right results with respect to diff test in section 3 of the homework. If you think that you should have the right answer and for whatever reason it's not turning green, please email me your output file. I will check your work, and if it is in fact correct in terms of the code, but for whatever reason your answer is not matching, I will just let you know what it should be. As long as you're able to execute the steps correctly, that's all I care about. I'm not going to penalize folks for having different versions of M+ that somehow give us different answers. I have found that the more complicated your model gets, the less likely it is that you get the same result across platforms as well as operating systems and software packages. All right. Can I show you some fun pictures? Because everybody looks a little sad this afternoon. So it was Halloween last week. So I wanted to show you what Halloween looked like at our house, in case, for those of you who hadn't seen it yet. So this is Huey and my better half. He is an Among Us character, which I had to explain to both of his grandparents what this was, but it's from a video game where he believes he's the imposter potentially, or not the imposter. It's unclear. We also have, though, some pictures from Halloween past I wanted to show. So this is our pumpkin. Jonathan made this. So props to him for figuring out how to make an Among Us pumpkin. This is my favorite Halloween ever. Huey was Santa Claus when he was 5 years old for Halloween, and this is the cutest thing ever. This was the pandemic year that he didn't get to go trick-or-treating in 2020, but he got to dress up and walk around his school playground and get candy and stuff. And then we also have one more I wanted to show you. I call this one Darth Santa. This is from last year when he had COVID on his birthday. Poor guy. So he still didn't get to trick-or-treat. But this year, finally, he got to go around the neighborhood and beg for candy. And yes, he has plenty of candy. We have lots of candy at our house. But we've got the Darth Vader costume. He's wearing a mask inside the house because he was sick, with the Santa bag. So, a hybrid approach. And in case you're curious, no, I did not dress up, but I could have. So this is, can you tell what's on here? Going to the Theta? It's a Theta hat. See, get it? I figured this class would get it. It's Theta hat. So this was actually swag from NCME many years ago when Jonathan was there and Terry Ackerman was the president. So emeritus faculty from our program trying to be funny. Theta hat. So next year I'll dress up as a nerdy psychometrician. I won't have to go to much trouble. This year I dressed up as tired mommy, also not having to go to a lot of trouble for that costume. But so we're getting there, folks. It's November. We have maybe a month of classes left, something like that. I'm hopeful today that we will finish enough of Lecture 6 and 6A so that you will have everything you need to finish homework 4. The invariance unit got condensed into 2 days, which I'm going to have to try to reconfigure to make that work, because I have 4 different examples on how to test invariance. But for those of you who are interested in differential item functioning, that is the same thing as what we call measurement invariance in CFA, and so that's why I have both types of models featured, hopefully starting next week. So any questions about schedule, assignments, anything else right now? Not yet? All right, then this is where we were last time, talking about graded response models. So this is how we would analyze ordinal responses using factor analysis. Question?
Yes, I have one.
Yeah.
In M+, when we are estimating this graded response model,
Mm-hmm.
we have the probits, right? If we want to find the probability of something greater than 1, if we are using any kind of thing, and 1 is the lower response,
Mm-hmm.
in that case, using that formula that you have here, that's for the red option, right? For zeros instead of 1, 2, 3 in this case.
No, the probability, when written this way, it goes with the blue.
Okay.
It's predicting blue instead of red in every case.
I tried that, and I had to take 1 minus the result of that in order to get the answer for greater than 0 in that case, for example.
That's probably because if what you have directly is a threshold, then that threshold is giving you the 0.
Ah, okay.
Yeah, the stupid threshold.
Okay.
So we can't forget the minus sign in front of it.
Okay.
So yeah, the threshold itself is giving you the red.
Regardless if that threshold is already negative.
So regardless of whether it's already negative.
Oh,
Yep.
okay.
So
Okay.
this is, so I'm half joking, but I'm actually serious. Like, I hate thresholds because they are internally inconsistent with the rest of the equation. The rest of the equation is talking about what happens to the predicted blue as theta goes up, whereas the threshold is referring to the predicted red. Like, it's out of sequence. So the negative sign switches it from red to blue so that it matches the rest of the equation. But yes, by itself, the threshold tells you either the logit or the probit of the probability of the red one. And you take the minus sign, and then that turns it into the logit or probit of the blue one. The 1 in each of these binary submodels. So whether you get logits or probits depends on your estimator. So if we're using full information maximum likelihood, can we have logits or probits or both, or either?
Both.
Yeah, we could have either one. In WLSMV limited information, then we're stuck with probits. So to get the predicted probability that corresponds to the predicted probit, you'd have to use some kind of inverse standard normal function to return the probability, or integration. So it's a little bit more painful to go from predicted probits down into probabilities, but the model still works the same way. Okay, let's see, where do we want to start? M+, example? Look at how to use this stuff. I think that's a good place to start. This is example 6a. So in, did I mention this before? Did I say that homework 5 is available? Did I say that? Okay. You can tell that I'm feeling a little scattered today too. So for those of you who are like, I feel like I'm running on a treadmill and I just want to get off, I understand. It's that point in the semester where we're all running on the same treadmill and we just have to keep going, or otherwise we're going to get run over. But we have homework 5 now available. It's not due until after Thanksgiving, so you have plenty of time to work on that. One of the things, though, that I'm asking for in homework 5 is a polychoric or tetrachoric correlation matrix. So this idea of how would we come to a different conclusion about how related our items are if we're using Pearson correlation as the basis for that versus polychoric. That's one of the things I want you to explore with your data. To estimate a polychoric correlation matrix, there's a variety of ways that you can do that. There's a log-core function in Lavon, for instance. In M+, the way that I did this was to estimate a saturated model as my model. So I asked for all of the thresholds and all of the covariances to be estimated, and then it gave me these relationships as covariances. I can then convert them into correlations in the standardized solution, and that's where these came from. So all of the files that I used to generate this handout are available in your download packet for example 6a. That way you can use them as the basis for running your own analyses. So it looks like most of these items are very highly related to each other. These are the same 7 items of physical and mental functioning for older adults, with the exception of item 7. And one of the caveats that I would want to remember in thinking about why item 7 is less related is that item 7 has less variability. So this was the item using the telephone. Most of the people in the sample can do this without problems. It's the easiest item that we have. So to the extent that we have low variability in an item, that in turn can translate into low covariability with other items. Last time we looked at model code with respect to setting up this confirmatory factor analysis for ordinal responses. And the key points to remember: categorical option. That's what switches it from regular CFA into CFA for categorical indicators, as it is called. This also switches it into the graded response model, as opposed to a 1PL or 2PL if you have ordinal data. The specification of which items load on which factors is exactly the same as what we've seen before. So the name of the factor by, or in Lavon it's squiggle tilde. And then we have the labels here that are then used subsequently down here under model constraint. So you don't have to do all of this to start with on your homework 4 or on your homework 5. Wait until you have a model that you're happy with and you want to report. Then you can use this code to create comparable item response parameters of A's and B's out of your IFA parameters that are estimated directly. The difference between the code on the left and the right is essentially right here. On the right-hand side, I have 1 L instead of 7 L's. So that translates into a constraint and not just a label. So all 7 loadings of these 7 items then are being forced to be one number, which I've labeled L. And to do a comparison as to whether that constraint is sufficient, that's our friend likelihood ratio test, because we're in full information maximum likelihood to start with. So comparing that HO value versus this one. Works out that the difference in -2 log likelihood is 135 on 6 degrees of freedom. So then what does this tell me? A significant model comparison between this version and that version tells me what?
The different factor loadings are needed?
The different factor loadings are needed. Correct. Now say the same thing with different words. Who else wants to play? Put discrimination in the sentence. Different factor loadings are needed, comma, indicating what about discrimination? Cough, cough, homework question. Zoomers, what do you think?
So is that saying that items discriminate, or the how do I answer this? There is variation in the amount of discriminating power between items.
Yes.
Is that
Yeah.
correct?
Yeah, I would say that's correct, although I would probably not stick power in the sentence because you might confuse people. Because power to test differences in discrimination is a function of sample size.
Yeah.
But yeah, holding these two, it would say that items vary in their discrimination. Otherwise, constraining them all to be equal would result in not worse fit. So this application is designed to drive home the point that if you have a question as to which model you should use, try to phrase that question as an empirical question via a model comparison if at all possible. So the original graded response model, as I have labeled here, is the 2PL version, where each item gets a different discrimination and each item gets its own set of difficulties or thresholds. I would call the analogous 1PL doesn't have a name. I'd just call it constrained, or the equal loadings version or something like that. But there's no reason why you couldn't test that same hypothesis in this framework as in models for binary data as well. And yes, constraining the loadings makes the model significantly worse, or freeing the loadings makes the model significantly better. I would phrase it either of those ways is correct. And the rest of our model fit here this chi-square test and this chi-square test we can't use. These are not valid because we don't have enough people to fill up the 7-way contingency table of all possible response patterns. So maximum likelihood gives us the optimal version of the parameters, I would say, in that it uses all of the original data. It assumes missing at random rather than missing completely at random, but it makes assessment of model fit a lot harder to do. So here are the results. Let's do this side first, left side. So we're in Logits, and this is the IFA parameterization that we get directly, which means we have factor loadings and stupid thresholds. So factor loading here is the change in the logit for a 1-unit change in theta. Given my identification, theta has a variance of 1. So that means a 1-unit change in theta means a standard deviation increase across people. So people who are 1 theta above 0 have an increase in their probability in logits of 6.8. So these numbers here are all in logits, which is why they're so big. I can tell you that they're significant, so p-value here, but significance is a very low bar in these models. We would expect that a loading would be significant. That's what we're interested in, is how the effect size for it. So the logit of the item response increases by 6.8 per change in theta of 1 standard deviation. Now, which item response? Because our choices are 0 versus 1, 2, 3, 0, 1 versus 2, 3, or 0, 1, 2 versus 3. Which of these submodels is this the loading for? All of them? Is that what you said? Yeah, you're right. Come back. Because it's loading sub I, or A sub I. So all of the submodels for the same item share the same slope. So the logit goes up by 6.8. What is it the logit of? Who cares? It's for that item. They're assumed to be the same. So there's only one loading given for each item, even though, as we go down here, each item has multiple thresholds. So item 7 looks like it's the least discriminating. Does that mean that I don't need it, maybe? Now, what else would I want to look at before coming to that conclusion? What do I have to keep in mind when thinking about what these loadings mean? Is it a bad item for everybody? Or relatively bad? Badder? No? Item 7 is super easy. It's going to measure people who are low on this trait. So I wouldn't necessarily say this is a bad item without looking at who it's bad for, who it's good for. And if I don't have any other items that are in that range, I would need to keep it. So keep in mind that these loadings are really talking about the range of the trait the item is designed to measure. Yes, where the difficulty is. So it's not necessarily a good or bad item, it's good or bad within a range. Now our thresholds. So I have 3 thresholds for item 1. How do I know how many I should have? In your individual data analyses, how many thresholds are you going to get back for each item? Number of submodels, yep. And how do I know how many submodels I need?
C minus 1.
Yeah, number of categories minus 1. So if I have binary data, that's one submodel, just one model. If I have 3 categories, that's 2. 4 categories, that's 3. So $1, $2, $3. It does not care what your original item response numbers are. It's just going first one, second one, third one, fourth one. So you could say that you have item responses of 10, 20, 50, and 100 as your anchors, and it'll be like, cool, 1, 2, 3. Where this gets confusing is in my data, these variables, items 1 through 7, the scale is 0 to 3. So the $1 is the transition from 0 to something else. $2 is 0 or 1 versus something else. So I did it that way so that the number after the $sign corresponded to what answer category it was referring to. So $1 is 1 or higher. $2 is 2 or higher. $3 is 3 in the submodels. And that's the way that I had it worded in this slide as well. In your homework and in most of your data, from what I could tell, you started counting at 1. So the answer choices in homework go from 1 to 6. So if I go from 1 to 6 as my answer choices, what does $1 then mean?
Greater than 1?
Greater than 1. Yeah, so it would be 1 versus 2, 3, 4, 5, 6. Then the next one is 1, 2. So what these mean is entirely contextual to your data. What if nobody answered the first option? What if I had 1, 2, 3, 4, 5, 6, and nobody answered 1? Could I do that? Is that okay? But then $1 can't be the transition from 1 to something else because I don't know where that would be. If I didn't observe category 1, I can't say at what trait the next ones are going to be more likely. So then $1 would be 2 versus 3, 4, 5, 6. So you have to know the frequencies of observations of each category to know what these mean in your data. I lucked out here, and all 7 items have all 4 categories used, so it simplifies things. Now this number, a logit of minus 9.8, that is the logit of a 0 when theta is at the mean. What does a 0 mean for this first submodel? It means answering a 0 instead of 1, 2, 3. So a negative logit of -9 means a very, very small probability, meaning that the probability that they can't do item 1 at all, the probability of the lowest response, is very, very tiny for somebody with average ability. For somebody with average ability, the logit of the next one over, so 0, 1 versus 2, 3, is minus 6.4. And then the last one tells us the logit of 0, 1, 2 instead of 3. So these thresholds describe the probability of the lower response option given a theta of 0. And if I say, I don't want a stupid threshold, I want to turn it into an intercept, what do I do?
-1. Time -1.
Yep, take it off. So now I have an intercept. 9.8 is the probability of 1, 2, 3 instead of 0 in logits. So the intercept tells you the logit of the higher category. The threshold tells you the logit of the lower category for each of these submodels. Missing proofing tools. Text in Portuguese is not being checked. You know what? I'm okay with that because I don't speak Portuguese. But thank you for interrupting my class to tell me that. Office is very considerate, wouldn't you say? All right, how are we doing? So it's very difficult to talk about like how relatively easy or hard these items are because using thresholds, because even though they're going in the right direction, they are talking about a prediction for the average person. They're not telling us who are these items designed for. So that's why I took these thresholds, divided them by their loadings, and made the IRT parameterization that's on the right side here. So now I have A's and B's. The A's are exactly the same as the loadings because our theta variance is 1. The difficulties, and I have them in a different order, so this is for all 7 items. This is the first submodel, then the second submodel. So just to note, it's by item over here, and it's by submodel on the right-hand side. So now, if I talk just about the first threshold, the first submodel here, minus 1.4 is the amount of theta you need to move from a 50% chance of saying 0 to a 50% chance of saying 1, 2, 3. For that same item, moving from 0, 1 into 2, 3 happens at a theta of minus 0.9. And then moving from 0, 1, 2 into a probability of 50-50 to get to 3 happens at a theta of minus 0.181. So each of these items now covers a range of theta with respect to where its difficulty is, potentially giving us more information than just a binary response would. However, all of these difficulty submodel values are negative. So what does that imply about who we are going to measure reliably with these items? Low people or high people?
Low people.
Low people. People whose ability is below 0. Because all of these refer to how much theta you need to be able to move into the next category. And all of these are negative. So if somebody has a theta of 2, for instance, none of these items are going to tell me about that person. The probability would be very close to 1 for the highest category for all of these items. So I still think the B's are much more useful. The extent to which they're differentiable, though, is also a question. They have to be in the correct order because this is a model that enforces order. So the second submodel is always going to be more difficult than the first submodel, and the third submodel is always going to be more difficult than the second. They have to be. If you have a question about whether or not that would be the ordering of the categories, this is not your model for that. This is assuming order. Okay, how are we doing? Okay enough? Here's some pictures. So here are some examples of what we call category response curves. So we're taking the predicted probabilities across the submodels, subtracting between them to get the probability of each distinct category rather than lumping them together. And these plots show then at each level of theta on the x-axis what the probability of each response category is. So item 1 is our most discriminating item. It appears to measure people somewhere between a theta of -2 up to about 0, based on where these curves intersect. So anybody with a theta of less than, let's go with, I guess, minus 1.5 is most likely to have a response of category 1, which is 0 in my coding scheme. People from a theta of minus 1.5 up to negative, just before negative 0.5 are supposed to have, most likely to have the next answer, and so on. So the boundaries of these, sometimes folks confuse with precision. So if I have a theta of 2.5, what is the most likely category?
4.
4. It has to be, because there's no 5. Ideally, if I wanted to measure high people better, I'd introduce a category 5. And then I would have the chance to split apart this range of the continuum, which is now currently all lumped together under answer choice 4. Likewise, if I wanted to measure low people even better, I would have to find a way to get something that's below category 1 to differentiate them. This is in contrast to a less discriminating item. This is item 7. Item 7 is covering a range of theta from about -3 up to about -1.8 or so. So where these curves intersect. And according to this item, 2 and 3 are basically useless. They're only the most likely categories in a very narrow range. If all of my items look like this, I might want to reconsider how many categories I had. But because they don't all look like this, then I wouldn't necessarily come to that conclusion. But steeper and more differentiated is what you want to have in these. Next picture down, this is item information. The way that I made this picture is to ask for it in M+, export the data into Excel, and make a prettier picture than what M+ provides. Inside the spreadsheet that goes with this example, there are written directions as to what the navigation of the windows are in M+ that generated these pictures. So please refer to that when you're making your own pictures. So item information is the amount of information per item, and they look kind of crazy because each item has multiple submodels contributing to its information. 7 down here is the one that's super flat. That's a consequence of 7's discrimination being very low. The other ones, like item 1, had the highest loading, but item 1 is only the highest relative to this region of theta. If I wanted to measure somebody with a trait level of, say, -3, the most information is from item 7. So each of these items is optimal under a certain range, and discrimination in that range, then, is what the loading is telling us about. The sum of these item information curves is test information, or total information. And this plot on the y-axis is information. I can convert that into reliability by taking it as information over information plus 1. So this then, if I were writing this up, I would say this measure has acceptable reliability if I define acceptable as greater than 0.8 from a theta of about minus 2.5 up until about maybe 0.5 or so, and after that it's not acceptable anymore. So we see a wider range than we did with the binary items, but we still haven't solved the problem that this measure is not going to be appropriate to distinguish people of high ability. And the thetas tell that story. So this giant pile of people at the end are people who can do everything. We don't have any items that are designed to separate them. If this were measurement in the context of a research study where we wanted to measure individual differences and predict it, this would be a problem. If this were measurement in the context of a screener for maybe recommending further testing for placement of older adults into assisted living, this isn't a problem. People who can do everything, I don't need to screen any further. The people who can't do everything are the ones that I would want to focus on. Okay, how are we doing? Questions? Everyone's quiet today. Hit me.
You have to. First, in the category response curves,
Mhm.
based on those curves, can we assume that, or what can we see here? For example, based on the x-axis, I can see that there we have just negative values. So I'm assuming that those two items are easy for these people. But at the same time, based on the steepness of those curves, I'm assuming that the first one is more discriminating and the a values say the same. But if we do not have those values, the a values, based just on those pictures, what can we infer from those graphs?
I would say that these items, the purpose of me making the pictures, I will tell you, is because item 1 is the most discriminating and item 7 is the least. And so I was trying to illustrate what the differences in prediction would look like for a highly discriminating item versus a not highly discriminating item. So the fact that the curves are less differentiated and less steep is a consequence of A being smaller. So if you think about like what would it look like if A were 0? Like everything would be flat, right? So somewhere between steep and differentiated and flat and on top of each other, that's your range of A. The other way that these items differ from each other is, as you said, in their location. So where on the x-axis these are located. So note that the x-axis on this picture goes from -6, whereas this one starts at -3.5. So this item 7 is less discriminating, but it is measuring people in a super low range of theta, whereas this item is not. And so that's why if you compare them, item 7 is this one that's on the bottom here. It's super flat with respect to its information because it's lowly discriminating. But there are no other items that are designed for super low people. So if you follow that item 7 all the way out to a theta, say, of -3, it is the most informative at that point. So it still would be worth including if your goal of measurement is to assess super low people, which in this context is what we would want to do.
Yeah, and the second one is, can we infer, for example, in the first plot, can you scroll? Yes, that one. For example, for someone with theta at level 3 or 4, can we assume that the most likely response would be 6, right?
Well, in this, it's 4. But yeah.
Sorry, yeah.
Yeah. Yes, you can, because there is nothing else for them to answer. So it's sort of a false, like, I'm 100% certain they're going to answer a 4. Yeah, because there's no other choices at that point. If you had extended the scale somehow to better differentiate people who can do it, right? Like there's more options for that, then we wouldn't know where somebody would fall necessarily.
Okay.
And I had made in your homework 4 pictures that look like this, and I have questions about them. So yes, this is directly relevant to inferences I'm hoping that you'll be able to make. All right. Let me show you some pictures then of the bees. So this is analogous to the example I had shown in the slides, but this is just for one trait for these 7 items. And this picture is sideways in that the items are on the x-axis, the latent trait is on the y-axis for the differences among difficulty, and in the top part here, the y-axis is discrimination. So item 7, for instance, is inarguably the worst item in terms of discrimination, right? But it still has relative value because in terms of the amount of theta needed to go from 0 to 1 to 2 to 3, it's covering a range of theta super low that none of the other items are covering. So it still has value from the perspective of coverage of this latent trait. The ordering of the transitions from 0 to 1, 2, 3, 0, 1 to 2, 3, and then 0, 1, 2 into 3, they will be in the right order according to this model. There is no option otherwise. But what's instructive to see is how close they are together. So for some of these items, like items 2, 3, and 4, there's not a lot of additional information to be gained in looking at whether it's 0 or 1. It's heading into 3 is the one that makes it different. Whereas 5, 6, and 7 are a little bit more spread out. So this is something that I'm going to ask you to look for in your homework is there a consistent pattern in terms of how useful your categories are? Because having more categories for people to answer is only helpful to the extent that they actually differentiate people in their abilities. So if I wanted to improve the measurement of people with a higher level of the trait, I would either have to come up with another response option that separates out can do it, or I'd have to come up with items that are more designed for people with higher abilities. Like, how often do you go running? Right? That would be a higher ability item. How often do you do your taxes by yourself? We're going to go with something cognitively taxing. How often do you play cards? Card games are, my parents love to play cards, and it helps, I think, keep them mentally in cognitive problem solving as opposed to just watching TV or other kinds of things. So this is the kinds of pictures that I have given you examples of how to make and that I would like to see in your homework as well. If you have another idea of how to present the same information, go for it. But I think pictures help to describe the idea that these items are located on a continuum and that each submodel has a distinct role to play in locating the item on a continuum. To do limited information estimation then is the last piece of this, where I'm still using the categorical option under variable, but I've switched the options under analysis to be WLSMV and using the theta parameterization specifically, which corresponds to probit. So error variance is fixed to 1 for identification under the scaling method. To do model comparisons using diff test, you have to do it inside M+. There's no way to export the data easily and do your own tests. So the way it works is the bigger model, we save the results to a DAT file, and then under analysis, that same file is referred to for the smaller model, meaning the more parsimonious model. So the bigger model with more parameters goes first, you save it, read in the information from it to estimate the model with fewer parameters, and then you get the results. So this is the same test of equal discrimination, just to demonstrate how to do nested model comparisons. We have the same code with respect to generating the A and B parameters, but they'll be in a probit scale instead of logits. And here's the output that we would get. So I have it spaced so that you can keep things aligned across the side. So the first thing that you will see is the chi-square test of model fit. So that is in reference to what? If I'm in WLSMV and I have a test of absolute fit, what is this against as my comparison? Think back to CFA.
H1?
H1. So in this case, H1 is not the means, variances, and covariances directly. It is the proportion of respondents in each category as the analog to means, and then what kind of correlation or covariance matrix instead? Polychoric for ordinal or tetrachoric for binary. So it's using the data estimated polychoric correlation matrix as the right answer. It estimated model parameters that are trying to recreate that as best as possible. And this chi-square test of model fit is then telling us how much worse than perfect our HO single factor model is. And in each case, it's worse than perfect. The diff test part is what shows up after you estimate the smaller model as an additional chi-square test. So it's labeled chi-square for difference testing, and this is the nested model comparison as to whether the single loading version of the model fit worse than the multiple loading version. And this gives us the same conclusion as in regular maximum likelihood. Yes, indeed, it's significant, meaning we made the model worse by constraining the loadings, meaning that the items are not equally discriminating. RMSEA is not as happy with this model, but CLI and CFI are. So in my results, I would probably have to say something like model fit was acceptable according to CFI, TLI, and SRMR, but not acceptable according to the absolute test of fit and RMSEA. Something like that. And then we get model parameters from the WLSMV version. These are in a different scale. These are in probits, which is why the numbers are different, but the patterns are very much the same. So item 1 is still relatively most discriminating. Item 7 is the least discriminating. The thresholds tell us the expected probit of the lower category when theta is 0. The fact that all of them are negative are an indication that our scale does not measure high people well. Converting those thresholds into difficulties tells us at what level of theta you have a transition predicted of 50-50 probability. In terms of local fit, let me scroll back up. Local fit, the residual option is what you can use to get, in M+, it doesn't give you normalized residuals, but it does give you residuals for the correlations, so the discrepancy in predicted correlation. You can also get your cheat codes to try and help you fix the model. I had a question about this. If I have a single factor model, the only type of parameter that a modification index is going to suggest is what?
Error covariances.
Yeah, error covariances is the only thing it can tell me, because there's no other factor that the items could load on. So the modification indices are always going to tell you how to fix the model that you have. They will never tell you that you need a new model. But if you see patterns in the residuals for the correlations and patterns that correspond, that, hey, these items all want to be more together and these items all want to be more together, that's where you would take the step then to potentially change the factor structure as a result of that. But in our case, here is the discrepancy matrix. So this is how far off in correlation metric each predicted pair of item responses is relative to what it was just estimated from the data versus what our model predicts. So I'm looking at these in terms of what is relatively large. So 6 and 2 want to be less together. 3 and 5 want to be less together. But in terms of how far off these correlations are, the largest is 0.07. I can live with that. So in your homework, I'm looking for you to mention, like, basically, what is the biggest source of local misfit, and is there anything that would be reasonable to fix it? In my case, I don't know how to make items 3 and 5 less related, and I don't know why they should be. So I'm not going to do anything to change my model. The way that I have written up this example is analogous to what I would want to see in your homework. That is, start with WLSMV so that you can easily assess fit. It's also instructive so that you can compare what happens when you fit the CFA versus when you do it the right way with ordinal models. Then once you have a model that you're happy with, then you can re-estimate it using full information, maximum likelihood, and logits so that you can get the better versions of the parameters and the potential factor scores. So WLSMV I'm viewing as a means to an end with respect to this. And so that's the way that I've written it up with these words. And you can again borrow these words for homework 5, so long as you change all the words in the right places. If I see forgiveness of situations in there or activities of daily living in there and that's not your factor, then I get to get grumpy. But otherwise, you can borrow my words. All right, we did it all. Hooray. Questions on this example? All right. Then I want to give you a brief tour of some other models that you may find useful, but that I'm not going to cover in any level of detail. Just a brief tour. So picking up on slide 15 for a little bit here. So the graded response model is the most flexible of the models for ordinal items in that each item gets a different discrimination, and all the submodel difficulties or thresholds get to be whatever they want. But if you're looking for a model that would take fewer parameters to estimate, which is a good idea if you don't have a lot of people, and your rating scale is the same across all the items, so the response format is exactly the same, then you would have a candidate for estimating what is known as a modified graded response model or a rating scale model. And this one is not directly available in M+ or Lavaan, but I feel like it could be if you could figure out the constraints needed to do it. And I've done that before and had some success, but I didn't want to present it this time. Basically, the idea of this model is that what you're holding equal are the relative distances between the difficulties. So rather than giving each submodel a distinct difficulty, we lock them down to be the same across items and estimate a common discrepancy between the submodels, the C parameters. So to describe this visually, it would look like this, where, and the bottom is our original graded response model. So for instance, item 1 might have category thresholds that are relatively spread out relative to 2 and 3, whereas a modified model would force them to be equidistant. So it estimates a common location parameter and then forces the distance from that common location to each of the submodels to be the same across items. So it saves a whole lot of parameters. That's called a rating scale model. It doesn't have a special name if you fit a constrained version where the loadings are constrained equal, but that's possible. Here's another one, partial credit. Now, I will tell you that from an interpretation standpoint, I like this one infinitely better, but for whatever reason, this link function is not built into most software, including Stan, for those of you in Jonathan's class. He just told me that this isn't built in either. The partial credit model uses an adjacent category link function. And so the submodels are not cumulative, they're only adjacent. So this, given the same response format of 4 choices, this one does 0 versus 1 as one submodel, 1 versus 2, and 2 versus 3. So to me, this is a lot more intuitive. What the difficulty parameters are, they're called step parameters because they're not the same as difficulty. They're given a different symbol, this delta, because they're not the same thing. But the model would look like this. So given that they answered 0 or 1, the first submodel predicts the logit of answering 1 instead. And delta, the location parameter, is the amount of theta it takes for 1 to become more likely. Not 50-50, just more. The second submodel tells you where 2 becomes more likely than 1, and the third model tells you where 3 becomes more likely than 2. So I think this is a lot more intuitive. It's not used very much in practice. Here are some pictures that would imply predictions from this model. So in this one, we have the probability of 0, followed by pink is 1, yellow is 2, and cyan, I think we agreed on 3 here. But this describes a misordering of the categories. So this is one thing that the partial credit model allows. In this prediction, the transition between 0 and 1 happens right here at a theta of like minus 1.5. The transition between 1 and 2 from pink to yellow happens back here. So according to this model, it takes less ability to get a 2 instead of a 1 than it takes to get a 1 instead of a 0. So that would imply potentially that what you're calling like the worst answer might not be the worst. So partial credit is used to test the assumption of ordered categories because it doesn't force them to be equal. So this idea here is called a reversal, It can happen if you have the ordering wrong relative to how it relates to the trait, or it can happen for categories that are relatively more infrequent. So if we look at the most frequent, the most probabilistic answer, there is no point where pink is most likely. It switches from blue to yellow to cyan, and pink is just hanging out on the bottom here. So I would not be as concerned about the fact that the transition from 1 to 2 is backwards. It just looks like this category of 1 is not useful. And you could probably get away with just 0, what we're calling 2, and 3 as your choices. Okay, does that make sense? Yeah, so if you're not sure about your order, so like if you have an item where it takes multiple steps to get it right, and they could get like none of the steps, they could get one of the steps or the other step, or they could get both steps, to where like the middle, you're not sure which is the harder one, this can help you decide that empirically. Here's a picture from my dissertation. So this picture was made, I'm going to say, goodness, 2002, give or take. And I'm trying to remember what package I used. I want to say it's PerScale, which is an SSI product that's probably not even a thing anymore. But what I had done is carve up continuous response time into categories because I didn't know any better, and I thought that I had to do that to fit some kind of latent variable model because all I knew at the time was IRT. And green is the easiest one and black is the hardest. And what these pictures are telling me, if you look at where the blues and pinks are, they are basically running along the bottom for every single item. Like there's no point on the trait for most of these where blue or pink are the most likely answers. Like I really don't need them. So that would mean basically what I'm modeling is either they got the answer right away or they just never got it at all. But very few people got it eventually. And so those middle categories are not as useful. Here's another example of an analysis using a partial credit model where the choices are strongly disagree, disagree, neutral, agree, and strongly agree. And fitting the partial credit model shows that the middle choices are pretty much on top of each other and even switch back and forth here. So for whatever reason, people are not viewing disagree, neutral, and agree as very differentiable in terms of where they are on the trait. Here's another one. This is a similar instrument, but it has a different response format. So we have choices of not at all and rarely, and blue shows the amount of the trait where rarely becomes more likely than not at all. Green shows where sometimes becomes more likely than rarely, and then orange shows where often becomes more likely than sometimes. And so these items don't cover very much of the trait. They only cover from about maybe -1 just past 1. And as a consequence of the fact that we don't have very good coverage, this is what the thetas look like. So here's a pile of people who said not at all to everything. My only way to measure them better is to come up with a lower response option than not at all. Can you think of any? That's a tricky one. The only one I can think of would be like, hell no. Like not only no, but never. I can't believe you even asked me that. Like that's the only type of response that would be lower than not at all. But what about on the high side? The scale tops out at often. Can you think of anything that's beyond often?
Always.
Always, almost always, most of the time. Take your pick, right? So an easy way to fix the high end is to give them another option. Not as many people are piled up on the high end, but there is a pile here. Could not applicable be an additional option? Oh, what a great question. That is an example that I linked to on my webpage that I don't have time to do this year, but actually Jihong helped me build it when he was my TA for this class at KU. There is a way to use not applicable as an answer choice. And the strategy is to hack your way into a model that you specify as nominal with a bunch of constraints where not applicable versus one of the other choices is a submodel, and then you would use the partial credit model for the other choices. So yes, it could be an additional option where not applicable would be estimated on an item-by-item basis. So not applicable could potentially be lower than these. It could be higher. It just would depend on the item and what not applicable would mean to them. So look for that as example 6B on the webpage. It's a tricky model to set up, but I think it could potentially be very, very useful. Also useful for missing data, because missingness could be informative. If somebody doesn't want to answer the question because of what they would have said, that's information. Rating scale model is partial credit with the same constraints on how far apart the categories are. So this sort of idea only in partial credit space. By the way, when people say partial credit, the original partial credit model, let me go back to the thing here. The original partial credit is a Roche model. So when people pick partial credit over graded response, I think it's because they want a Roche, all the items are equally discriminating type of model, but the generalized version adds the differential A across these. So that's the part here that extends it into something that looks more like a 2PL. So I told you a brief tour of all the other ones. One of the reasons partial credit models don't get used is because each submodel doesn't use all the available data. So it can be harder to estimate the transitions for categories that are used less frequently. Nominal is the other one that you should be aware of. Nominal is for unordered categories where no one would ever say they're ordered. So like, what would you do in this situation? Those kinds of answers where there's not a right answer per se, but some choices might be more related to the trait. So if somebody insults you in public, how do you respond? Do you walk away? Do you insult them back, or do you hit them? Right? Like those kinds of choices. Now, I'm not going to say there's a right answer and a wrong answer, but if I'm using this type of item to measure aggression, then odds are good more aggressive people are going to answer, yeah, I'd punch them, and less aggressive people might walk away. So in a nominal model, the submodels are arranged like dummy coding, where one of the answer categories is the reference, and the submodels tell you the probability of answering the other category relative to the reference. What makes these different in terms of their estimation is that each submodel has a different slope. So how discriminating punching someone versus walking away can be different than how discriminating insulting them back versus walking away is. So each submodel has a different A and a different B. There are two different parameterizations of this model. The dummy code one is the one that I wrap my head around the most easily. There's another one where all of the B's have to somehow sum to 0, I think. And there is an article on your reading list. The first author is Revuelta, who wrote a tutorial about these models and how to fit them in M+ and showed the different parameterizations, and I really liked that article. I thought it was very useful in understanding these models. Where nominal response models would tend to be used is in multiple choice items where people want to examine the usefulness of the distractors. So like something like this would be, people who are low on the trait are most likely to pick D. They're next likely to pick C. People who are high on the trait are most likely to pick A, but if they don't pick A, they're going to pick B. So this can help you get more information out of what is otherwise a binary answer if you look at how theta relates to the choices of which distractor people pick if they're incorrect. So that can be useful in an education setting as well as in any kind of measurement setting, I would say. There. And then last but not least, any kind of outcome can be a latent trait model. So for instance, there's counts. Example 6C walks through all of the possibilities for count models. Poisson, negative binomial, zero inflated Poisson and negative binomial, and the hurdle variance that split if and how much. Example 6C walks through those choices within M+. But the bigger picture is that if you can predict it, you can put it in a latent variable model. There's never a need to take an outcome and either cut it up or otherwise distort it. We just have to find the right link function and conditional distribution to make it work. And that's my big picture. Ta-da! So don't do what I did and cut up response time. I didn't have to do that. I just didn't know any better. But it got published. Yeah. So add that to my list of things I've written that are now wrong. All right. Questions? Anything that you want to hear more about that I glossed over too quickly? Zoomers, you've been awfully quiet. Cass, did I answer your question well enough about not applicable?
I think so. I'm gonna take a look at the example 6B, so I mean, if maybe no one has any questions, if you can bring that up quickly, walk through it.
I can try to, yeah. How quickly it will be brought up is the question, but I linked to where I last covered it, which was this class at KU in fall 2018. Note that the page looks remarkably similar. I'm a creature of habit. It's example 6B. So there's an example that, yes, Ji Hong, who just defended his dissertation, helped me build with this, so he may be more familiar with this code at this point than I am. But for an example, here's an example nominal response item for who are you going to vote for, very timely for this time of year. There's two parameterizations of nominal models, so yes, the sum of the A's and the sum of the B's have to equal 0, which is 1, or we set one of them to 0, which is the reference category. The idea of, let me see if I can do this quickly. Yeah. So these are example data where there's different choices for things that what I think people can prioritize and what they picked. These are category response curves describing how that relates to some latent trait. The not applicable is, this is what it's called. That was the word I'm looking for. Semi-ordered partial credit model. So there is a line of research, Corinne Huggins Manley is the lead author on that, and one of the articles is on your reading list for how to fit this model. And so this is where, this is measuring a acculturation in a sample of persons who are of Mexican origin who are living in the United States. And there is a not applicable option as part of the scale. So rather than just throw those responses away or treat them as missing, we can include that as part of the measurement of our trait. So the choices then are not at all stressful, a little stressful, somewhat stressful, quite stressful and extremely, or does not apply to me. So then essentially what this model does is take this part of it and fit a partial credit model. So it's thinking of these as not enforcing order, but could be ordered. And so then each of these are part of submodels where it would be what's the amount of theta you need to go from this one to that one to this one, that one to this one to that one. And then this one, this separate does not apply. It's the logit of answering this as opposed to one of these is a separate submodel. So then you have a separate discrimination and a separate location for where does not apply is with respect to the theta continuum. The code for it is ugly. So he has descriptive statistics for how often that was selected. It wasn't a very common, actually not applicable was the most common for some items. We also have missing on this one. Here is the logic of M+ code that goes through it. And there's a whole bunch of labels and constraints that have to happen. And in nominal data, it's the pound sign that labels the submodels, and they're intercepts instead of thresholds. So at least we don't have to deal with stupid thresholds within this system. But this, there's a whole lot of constraints that it takes to make this happen. And so you can walk your way through the handout that describes all of this. I would not recommend this for homework 5, by the way. This is a higher level of complexity that I'm expecting out of anyone. But this is more like for your reference down the road. I feel like this is the optimal way to use additional answer choices that are not ordered along with answer choices that are ordered. So this is that, and there is a video that goes with it, if I remember correctly. Yep, we did have a video for that. The 6C doesn't have a video, but this one is talking about count outcomes instead. And there's a lot of words in the handout, so it should be okay. There. 313. Is that better?
Did you model missing data as well, or?
I don't think so. If I remember correctly, we did not, although there's no reason why you couldn't. So I think that using this for missing responses is potentially informative when people skipping the question is telling you something about their trait.
Right, so like when it's NMAR.
Yes, missing not at random, or not missing at random, whichever version of the acronym. Yep. Yeah, and that would have to be like if they skipped all the questions, that's different than like they just skipped this one. Because I think just skip this one would be indicative of a mechanism that why that one.
Right, and I guess you couldn't infer that it may have been non-applicable, it could have been for some other reason, right?
Yeah, and that's one of the topics that I skipped in this semester that I want to get to towards the end instead is like, what are the implications of these model choices for how you would build a survey? And one of the take-homes would be, do not let people guess what they should do, right? Like, not applicable should be a choice. And any other reason why someone, like, prefer not to answer, make that a choice. So that you're not guessing as to why the data are missing. Because these sorts of advanced models can be used to use that information. So, all right, 3:15. Anything else before we call it a week? Not just a day. A week. All right, thanks for being here, everybody. Let me know if you need anything with homework 4, revisions to homework 3, or otherwise. See you next week. Bye, folks.